So this is where we left off last time. We've got our three particles in a harmonic oscillator potential. We've got them with different initial conditions, but they're all responding to the same K spring stiffness, so they are moving with the same frequency, so that's pretty cool. We want to start building out the forces that act on these things. So if I go back over to the article that we're referencing, this 2017 article found in Physical Review Letters, that's just this little part here. I think what I'll do this time is add in the damping force and the driving force. I think that would be a fun thing to add in next, and we'll save this this rate business, this rate bonding until later. So let's add in these two. So we need to have a drag force. So let's see here, we'll call this drag coefficient. Actually, no, let's call it B to match the equation. Then I'll give a little comment to say what it is. So this is the drag coefficient. Let's make it small for now. So this is the drag coefficient. Actually, let me double check this. It looks like here they've got the same drag coefficient on every particle. That's interesting. I think they made these. I guess they are the same species, aren't they? Because they have the same mass there. So maybe they're working with the same species. Well, we can change the species on these things. So this is also the harmonic oscillator well spring stiffness. I'm throwing every possible name on there so that I remember what it is later. Of course, K is usually the spring stiffness. B is usually a drag coefficient. So let's do this part here. We've got the well here. Let's do the drag force next. Particle.net_force. And I'm probably going to get the comment that that Python will accept plus equals as a shortcut for this thing. Except that the way they've set this up in GlowScript, it doesn't seem to work when vectors are involved. So if somebody has a workaround for that, I'd appreciate it. Otherwise, I don't mind writing it out. It's not. I mean, I only have to write it once. So this is going to be a drag force. So a damping force. Yeah, drag force is usually proportional to velocity squared. This is a damping force because it's velocity to the first power. So let's see here. So we'll put in the particle's velocity, and the direction's already taken care of because it's always going to act opposite of the velocity. So I just put in B times the particle velocity. Oh, and then I need to divide by No, I don't divide by particle.mass. That's down here. Yeah, so this is the force. Yeah, the force is just negative BV, and that's what I've got over here is negative BV. So let's run this and see how long it takes for these folks to slow down significantly. Okay, so they're slowing down. They're definitely decreasing in their amplitude. They also look like they're going more slowly. Now, of course, under this model, you can think of it like they're losing a certain percentage of their energy each go around, and so it'll never fall exactly to zero, but it will fall so close you won't notice it. Yeah, these two are starting to overlap now, so eventually they'll all just sort of be overlapped, which is kind of fun to watch. Excuse me. All right, so with that, we can add in the next piece, which is a driving force. Now here, for the sake of simplicity, they're only driving one of the particles. And that particle is sort of sharing that extra input of energy through all of the bonds formed with these, formed with the other particles. So let's set it up to where we just have one of the particles being driven. So let's see here, define well properties. So now we need to look at the driving force. So let's pick which of these is going to be driven, and I choose, well, let's just match what they have. Let's go with 0. So let's see here. Let's try, let's call this ID for I driven. So this is the index of the particle to be driven by external force. There might be an easier way to code that into the list itself, but for right now we'll just have it be the 0th one to match the nomenclature in the article. So I've got ID equals 0. It's the index of the particle to be driven. And so what I need to do here is I need to look at, oh, and this is where, okay, and this is where I need to change how I'm looping this, because currently I don't have their index on here. Unless there's a way to access that, because this is so much cleaner rather than having a you know, the list on here, or excuse me, rather than having the index on each of these. I wonder if there's a way to do that. Let me check on that and find out. You know what? I changed my mind. I am going to change how this loops, because eventually in this I'm going to need to loop over the particle list twice for the bonding. So I may as well go ahead and get the index here now. So party is over for now as far as not having to worry about the indices. So let's say this is I of particle is equal to 0, and then we'll have, well, I guess I can do, for I particle in range 0 to length of particle list. I think that's how you do that. So let's say particle underscore list I underscore particle. See, this is why I didn't want to do this, is it makes it so much longer, but it's what we have to do. So plug that in there, paste that in here, paste that in here, paste that in here. I haven't gotten any complaints yet from VPython about going beyond this line, but we'll see what happens. So now what we'll do is we'll say if I underscore particle equals 0. So this is the first particle. Then what we want to do is we want to add on to this net force the driving frequency equals, same thing, plus a driving frequency. So this is, so I need an amplitude and then sine of omega dt. Okay, so I need drive amplitude times sine of omega d times t. Now I'll need to do a few things to be able to use that. So this is the driving force on particle 0. So this is the driving force on particle 0. So I need to set up a few things. I need to set up drive amp and omega d. We'll copy those so I remember what I called them. And I need to set up the time. So let's go time equals 0, time, okay. And then I need to update time here. So this is going to be time equals time plus plus dt. So this is update time. So we'll look to see if I did this correctly. If I didn't, I'll have to fix it in the next video because we are getting close to the 10-minute mark here. So let's see here. So I need something called drive amplitude. Let's make that smallish. So this is driving force amplitude for particle 0, and this is, let's see, these things are going to naturally have an omega of root k over m, so that's going to be root 1 divided by 1, and that's going to give you an omega of 1. So let's make this one a little bit slower. So this is going to be the driving force angular frequency for particle 0. So what you're going to see is the particle 0, this one that starts in the middle, is going to get this driving frequency. So it's going to keep going even though the others eventually slow down. Right? Did I set that up right? I'm adding to this. Yes. Good. On we go. No error, no error, no error, no error, no error. Stop. There we go. And of course it's gone. Oh, I need to make this thing a vector. Oh man. Oh, y'all have been yelling at me about that for a while now, haven't you? Okay, so we're gonna go vector that, comma 0, comma 0. I'm kind of surprised it made it in NaN and not just a, and didn't give me an error. That's because usually it gives you an error when you try adding scalars to vectors. Okay, that's better behaved. Let's change this back to while true. Let's change this thing's amplitude back to something more reasonable. Oh, y'all have been yelling at me about that for the last couple minutes, haven't you? Yep, there it goes. Now it's going slower. I guess I changed the rate. Also, printing to the screen slows things down a bit. So let's get rid of that print statement. Our diagnosis there is done. Let's put in a rate of 100. Saved. Run it. Okay, cool. They are going back and forth better as expected. You notice this one's going farther than it did before because it's being driven. You also notice it's going at a different frequency than the others. And I'm having trouble keeping track of which one it is, so let's make this one its own color. Let's make this one white. So this is the driven particle. And while we're at it, let's go ahead and make them all different colors. I probably should have done that in the last video. That would have been easier to see. And just because I am running short on time, let's make the rate faster. Yeah, so you see, the white one, the driven one, is going at a different frequency than the others, and while the red and the green are slowing down and are eventually going, you know, they're leveling out to here, the white one continues on at the driving frequency. And this is kind of cool. This is kind of a cool animation. Yeah, I might have to overlay a club beat to this or something. I don't know. All right, so thank you so much for watching. I will see you next time. Bye-bye.